Hello everyone. This video is based on a nucleophilic substitution and elimination reaction. Most importantly, competition between nucleophilic substitution and elimination. The main purpose of this video is whenever reagent and reaction conditions are given, whether that particular substrate undergoes elimination or substitution. In most of the times, both the reactions are definitely possible, but which is major, which is minor, in order to solve those kind of questions, this video will definitely help you. And let us get into the video. In order to understand the competition between SN and elimination reactions, first you have to know SN2 and E2 conditions, because these two reactions are always in competition. In case of SN2 and E2 reactions, concentration of nucleophile or concentration of base, it should be high. So here high concentration of nucleophile and base. Strength of the nucleophile or strength of the base, it must be strong nucleophile or a strong base. And what type of solvent we generally use in SN2 reactions or E2 reactions? That is polar aprotic solvent. Polar aprotic solvent, that is DMSO, dimethyl sulfoxide. We also use acetone, polar aprotic solvent. Even we use dimethyl formamide, DMF. In fact, we also use dimethyl acetamide. Need not to remember so many. These four solvents are commonly used in SN2 and E2 reactions. And if you observe rate law of SN2 reaction and rate law of E2 reaction, so rate law of SN2, that R is equal to K into concentration of alkyl halide into concentration of nucleophile. With respect to alkyl halide, with respect to even nucleophile, it is a first order. Overall order of the reaction is 2. If it is E2 reaction, R is equal to K into concentration of alkyl halide into concentration of base. Again, with respect to each, it is a first order. Overall, it is a second order reaction. And if you also observe relative rates of alkyl halide in SN2 and E2 reactions, in case of SN2 reaction, it proceeds through pentavalent transition state, Walden inversion product, backside attack. Steric hindrance is the key point. Therefore, in SN2 reaction, primary alkyl halide is more reactive than secondary alkyl halide. Secondary is more reactive than tertiary alkyl halide. In fact, tertiary alkyl halides, they do not undergo SN2 reaction. Simply we have to say they do not undergo SN2 reaction. And if you see E2 reaction, in case of E2 reaction, reactivity is based on the stability of the product. Tertiary alkyl halide forms more stable product. Therefore, the order of reactivity, tertiary alkyl halide greater than secondary alkyl halide greater than primary alkyl halide. So this is the order of reactivity of alkyl halide in SN2 reaction and E2 reaction. Now let us take some useful information before solving questions on SN2 and E2. These are definitely not the rules, these are only hints. I have observed so many examples from the standard references. By observing all those reactions, whatever the products they have given, based on that, I'm giving some hints. But once again, these are not the rules, these are only the hints. The species acting only as nucleophiles. There are some species which act as only nucleophiles. In that category, you have a halide ion, chloride, bromide, iodide, cyanide ion, Cn minus, SH minus. It acts as only nucleophile. And even one more important example I found, that is acetate ion. So these examples mostly they act as nucleophiles. So obviously nucleophilic substitution will be favorable. There are some species which act as only bases. We have DBU, DBN, DBN. This is also acting as only base. And most importantly, tertiary butoxide, due to its bulky size, it cannot act as nucleophile easily. So whenever these species are given, it's better to go for elimination rather than nucleophilic substitution. In case of these species, you will get substitution product. And the problem is with particularly two kind of species, that is a strong base and a strong nucleophile, that I found is OH minus and also alkoxide. Alkoxide mostly you will find a methoxide and ethoxide. The problem is only with these species, hydroxide and alkoxide, particularly in case of alkoxide, methoxide and ethoxide. So these species are strong nucleophiles and strong bases. Now let us move on to applications, how to apply this particular theory. So let me take the first example here. It is a primary alkyl halide. The given species is a strong base and strong nucleophile. In case of primary alkyl halides, if you compare SN2 reactivity and E2 reactivity, primary is more reactive than secondary, secondary is more reactive than tertiary. In case of E2, tertiary is more reactive than secondary, secondary is more reactive than primary. The given species is primary alkyl halide. Primary alkyl halide is more reactive in SN2. Therefore, here you will get substitution product. Under SN2E2 conditions, N-propyl bromide on reaction with methoxide, it gives a substitution product. And here, this is a primary alkyl halide, strong nucleophile and strong base. Due to steric hindrance, so the reaction is taking place here. There is some bulky group here, isopropyl group. Due to that steric hindrance, even though SN2 is primary alkyl halide, SN2 is more favorable. Due to steric hindrance, here elimination takes place. So because of that, the major product will be isobutylene. I am writing only major products here. And one more example here, if you see, it is a primary alkyl halide, but the species is a strong base and strong nucleophile charged species. But due to steric hindrance, nucleophilic substitution is difficult. Therefore, it will undergo E2 reaction. Totally, you can see 1, 2, 3, 4, 5 carbons are present. And here it causes elimination, and the product will be Zaitsev, not Zaitsev product, that is a Hoffman product. The product will be Hoffman product. Next example, if you see secondary alkyl halide, I already told you acetate ion acts as only nucleophile. Therefore, here the product is a nucleophilic substitution product. Even for this reaction, we have practical evidence. 100% in this example, we get a substitution product. Next one, again 2-chloropropane, that is isopropyl chloride, but when you take alkoxide, already told you hydroxide and alkoxides under SN2E2 conditions, major product is elimination product. Major product is elimination. Here both are possible, but major product is elimination product. So here this is major product. Even for this we have practical data. So this is alkoxide ion causing elimination mainly when compared to nucleophilic substitution. And in this, if you see hydroxide, already told you the problem is with hydroxide and alkoxide. In case of SN2E2 conditions, when we use hydroxide and alkoxide, secondary alkyl halide if you take, secondary alkyl halide. I'm not talking about primary alkyl halide. Secondary alkyl halide, both are almost equally reactive, but main product, major path is elimination, and here the product is propene, so that is major product, and nucleophilic substitution, isopropyl alcohol, that is minor product. Here this is major product. And most importantly, the same condition, isopropyl halide, OH minus, if temperature is high, the percentage of elimination product further increases. So here these are the products we are getting. For example, here I am writing X percentage, this is Y percentage, this is Z percentage, and this is some P percentage. No doubt here X is greater than Y and Z is greater than P. Most important thing is Z is greater than X, you have to know. As temperature increases, the percentage of elimination product will increase. And if you see a tertiary alkyl halide SN2 is not possible. Therefore, it undergoes only E2 reaction. Hence, the product will be isobutylene. Now, let us discuss the same for SN1 and E1 conditions. But when compared to SN2, E2, it is somewhat easy. Concentration of nucleophile or base, if you observe for SN1 and E1 conditions, low concentration of nucleophile or base is preferred. Strength of nucleophile or base, we prefer weak nucleophile or a weak base. Solvent, if substrate is neutral, if substrate is not charged, in that situation polar protic solvents are preferred. Examples: water, alcohol, carboxylic acid. Particularly if solvent is used as a nucleophile, that reaction is known as solvolysis. And the rate law of SN1 and E1, if you observe, you take either SN1 or E1, rate law R is equal to K into concentration of alkyl halide power 1. It is first order with respect to alkyl halide. Nucleophile or base does not affect rate directly with the help of concentration. It is not actually appearing in a rate law. If you see the reactivity of SN1 and E1 reaction of different alkyl halides, so tertiary alkyl halides are more reactive than secondary are more reactive than primary. Even in case of E1 reaction, the same order is found, tertiary is greater than, secondary is greater than primary. In fact, all those details you already learned while studying the mechanism of SN1, E1, SN2, E2. This video is exclusively on competition between nucleophilic substitution and elimination. So, based on the theory what you learnt in those mechanisms, we are just using those factors or those favorable conditions to solve the different questions. And if you see the example, a tertiary alkyl halide is given, SN1 E1 conditions, solvolysis reaction, SN1 reaction, tertiary is more reactive, E1 reaction, tertiary is more reactive. Since it is tertiary alkyl halide, SN1 and E1 both are possible, but under these conditions, even though both are possible, substitution is more favorable than elimination. Elimination is also possible, but substitution is more favorable. Therefore, some percentage of substitution product will be more. If temperature is mentioned and if temperature is high, in that situation you can go for elimination product as a major. Now let us apply the theory. The first example is secondary alkyl halide, NaOET. I already told you, hydroxide and alkoxide. Even though SN2 and E2 are possible. In case of hydroxide and alkoxide, elimination is major product. Since it is not bulky base, jades of product will be produced. So this is the major product, trans 2 pentene. Next one, Cl minus, it acts as only nucleophile. Therefore, the product will be, this is the product, 2-chloropentane. SN2 reaction, stereochemistry is inverted. Now if you observe example 4, tertiary alkyl halide, tertiary butoxide, SN2E2 conditions. SN2 is not at all possible. Here elimination product, Hoffman product will be produced. So this is the product, that is 2-cyclohexyl propene. Again tertiary alkyl halide, DBU, DBN, they are only bases. Therefore elimination will take place. The product will be Hoffman elimination product. Primary alkyl halide, I gave the hint, DBU, DBN, they are only bases. Therefore, elimination product, 1, 2, 3, 4 carbon atoms are present. So, this is butanene. NaSH, SH minus, it acts as only nucleophile. Major product is nucleophilic substitution. Now, let us take example number 8. It is a primary alkyl halide. Conditions are SN2E2 conditions. In case of primary alkyl halide, SN2E2 conditions, SN2 is favorable. Therefore, here the product will be nucleophilic substitution. Example number 9. Again it is a primary alkyl halide, NaOET, SN2E2 conditions. Major product is substitution product, nucleophilic substitution. Secondary alkyl halide, the problem is with hydroxide and alkoxide. I already told you, even though SN2 and E2 are nearly equally possible, but with hydroxide and alkoxide, elimination is major product. Hence, the product will be like this. So here that is the Jadesef product. The secondary alkyl halide, NaOMe, that is strong base and strong nucleophile, SN2E2 conditions, elimination is the major product. Therefore, here the product will be this one. In fact, trans product you will get. Next, secondary alkyl halide, this is the most important case. Secondary alkyl halide, OH minus, SN2E2 conditions, elimination is major. But here if you observe, hydrogen is above the plane, but of course at this position both the hydrogens above and below are possible. But E2 reaction, it proceeds through anti-periplanar transition state. The two eliminating groups must be opposite. But here hydrogen stereochemistry is not supporting. Therefore, here the product will be next 13 OTS. It is also a good living group. In fact, its living ability is more than halide. Same conditions you can apply. This is a secondary derivative. OH minus, OH minus and RO minus, strong nucleophile and strong base. But in case of secondary alkyl halides, we follow elimination as major. Since it is not a bulky base, we have to go for a Jadesef product. Secondary, this is also secondary derivative, but SH minus is a strong nucleophile. Therefore, nucleophilic substitution will take place. OTS, DBU is a strong base. Here again stereochemistry is important. The two eliminating groups must be opposite. So here this is OTS, hydrogen, but DBU, not only stereochemistry, here DBU is a bulky base. Therefore, in case of that elimination, the product will be, this is the product. And the next one, secondary alkyl halide, NaOH, elimination is major, substitution is minor. And in case of tertiary alkyl halide, SN2 is not possible. So this is a SN2E2 condition. Elimination will take place. That is the Jadesef elimination, Jadesef product. Tertiary alkyl halide, tertiary butoxide, bulky base, elimination is possible. So this is the product.